Okay, so it's a great pleasure to introduce Tony Pantev of Penn. And he's going to talk about geometry and topology of wild character varieties. And he has 135 slides.
Yeah, no, 95 only, but
95.
Okay. Thank you. Yeah, it's great to be able to speak here. So I was struggling, trying to decide what story to tell, and finally decided to go a combination of something mildly new and something not that new, just so that there is some kind of a coherent picture emerging from this. So here is an outline of what I plan to do. I'm not sure if I'll get to the end, but first of all, yeah, it's based on a sequence of joint works. The geometric part is some new work with Arinkin and Toen, and then the topological part are a sequence of works that we wrote with Emmanuel Diaconescu and Ron Donagi, and with Chuang, Diaconescu, and Ron, and Satoshi Nawata. So I'll start by reviewing the wild character varieties, recalling what they are. Then I'll talk about their geometry and explain how we can use some kind of homotopical algebraic geometry to resolve their singularities and to construct Poisson and symplectic structures. And then I'll switch to discussing their topology and discuss conjectures about their Euler characteristics and the weight of Poincare polynomials, as well as a physics strategy for actually proving those conjectures by converting the question to a question about counting BPS states on Calabi-Yau manifolds and or some gauge theoretic calculations, or computing refined torus knot invariants by using Chern-Simons theory. And so that's the plan. Now let me start with introducing the main objects that we would like to study. And these are the wild character varieties. And what are these character varieties? So character varieties are just moduli spaces of matrices, but very special moduli spaces of matrices that arise from representations of fundamental groups of Riemann surfaces. And they parametrize monodromy data for systems of linear ordinary differential equations on compact Riemann surfaces, and the systems will have analytic or meromorphic coefficients. And those guys historically come in three flavors. They could be unramified, tamely ramified, or wildly ramified. And so unramified means that we are dealing with flat connections that locally on the Riemann surface look like the Ram differential, and then some matrix in the local coordinate which has meromorphic convergent power series as coefficients. And so the unramified case is when actually it's homomorphic. The connection matrix is homomorphic at every point. The tamely ramified case is when we are allowing poles, but only first order poles. And the wildly ramified case is when we are allowing higher order poles. And so if in the ramified case, what we are dealing with are representations of the fundamental group of the compact Riemann surface. And if you choose a basis of generators for the fundamental group, you just want to assign to each of them a matrix, and those matrices have to satisfy the relation in the fundamental group, which is that the product of their commutators is 1. In the tamely ramified case, you are allowing punctures where the poles are appearing, the first order poles are appearing. So you get extra generators in the fundamental group that go around the punctures. And then for the monodromy representation, you're looking at collections of 2G matrices plus K more matrices for the punctures. And the relation now becomes that the product of the commutators for the A and B cycles matrices plus the matrices corresponding to going around the punctures, that product is entirely equal to 1. And in the wildly ramified case, the collections of matrices that you need to look is more complicated. So I'm gonna talk about that now. So for the wildly ramified case, it's a little bit more complicated because the actual monodromy of the connection is not the only invariant of the connection. You need additional data in order to specify topologically the data of the connection. So what are we dealing with? The background data that we are dealing with is a smooth projective curve X, that we have a number of distinct points. These are going to be the poles of our connections. We have a complex reductive group G with a Lie algebra Gothic G. And I'm going to fix some invariants that control the behavior of my differential equations of my connections. Those invariants is what's called the irregular type of the connection. So for each of the punctures, I'm going to fix Laurent polynomial. So the k Laurent polynomials Q1 to Qk, which will be the fixed conjugacy classes of the Laurent tail of the connection. And I'm also going to fix a matrix, which is going to be the formal monodromy for the connection around that point. And so I'm going to study connections V nabla. So these are going to be principal G bundles V and meromorphic connections nabla, so that the polar part of nabla at each of the punctures is given by Qi, and the formal monodromy of nabla, and I'm going to say a little bit about what the formal monodromy is in a moment, is given by the given fixed conjugacy class, belongs to the given fixed conjugacy class. So in a little bit more detail, what is the irregular type? So if you have a group G, a G-valued irregular type is a Laurent polynomial. So it's just the negative part of the connection matrix at each puncture. And it's a polynomial in Z inverse, where Z is the local coordinate, with coefficients in the Lie algebra. And in fact, you can take that polynomial to have coefficients in the Cartan algebra. And then the requirement is that locally the connection is gauge equivalent to D plus the derivative of that polynomial. So this only captures the second or higher order pole behavior of the connection by the way I'm defining it. And I'm requiring my connection to look like D plus dq in a local trivialization near the puncture for some finite root of the coordinate. And so the reason we can take our coefficients to be in the Cartan subalgebra is because there is a structure theorem in the study of meromorphic connections, which says that up to a Puiseux gauge transformation, we can always convert the polar part of the connection for Laurent polynomials of degree -2 or lower to be with coefficients in the Cartan. So I'm always going to assume that my regular part is given by these types of polynomials. So now what do we do in order to convert this to topological data? So you have to replace your surface by a surface with boundaries. So you take the real oriented blow up of the compact surface at the punctures, at the mark points. So you replace just each mark point by a little boundary of a disk that you're deleting from the surface at the point, centered at the point. And so you're replacing the mark point by a boundary circle di, and it parametrizes the real oriented directions emanating from xi. So as I said, this is a surface with boundary, and there are k boundary components d1 through dk. And each irregular type actually can be used to decorate X with some additional data. So one thing that the irregular type gives you, it gives you a connected reductive subgroup, Li, contained in G, which is the centralizer of Qi in G. So you take all those matrices in the Cartan that are the coefficients of Qi and look at the centralizer of those matrices. And that's some reductive subgroup in G. It also gives you a finite subset in the boundary circle. So this breaks the circle into arcs, and the points that break the circle into arcs are the singular, or they're called the anti-Stokes directions. And for each anti-Stokes direction, you also get a unipotent subgroup corresponding to that direction in G, which is normalized by the reductive subgroup Li. So if you fix the irregular type and you study the asymptotics of solutions, of convergent solutions of your connection near the puncture given by that irregular type, you get this data. So you get a reductive group, you get breakage of the boundary circle into arcs, and for each point that breaks the circle into two arcs, you get a unipotent group that normalizes that reductive subgroups. And I remind you that in order to write the irregular type in the way I wrote it as something with coefficients in the Cartan, I had to actually extract the root of the local coordinate. So we do get a reductive group, but that reductive group actually by itself depends on the choice of a root. So if you really want to get something that's independent of any choices, you get actually a little local system of reductive groups with a cyclic monodromy on the original circle. This is without extracting the root. Okay, and so you can use this data to produce a new surface with a little bit more topological fuzz in it. So I'm going to call it X twiddle. So this is the one that you define by looking at the original surface minus the punctures, and you puncture that once near each singular direction. So this is the picture. You can, so this black thing here is the boundary that I introduced by deleting the puncture and looking at the reoriented blowup. Then on each of those boundaries, I can on this boundary I can delete a point near each of the anti-Stokes directions. And I still want to remember that this is a surface with boundaries, so I'm just going to glue a little annulus to that boundary. This is this yellow guy, this yellow color that I'm adding, stretching a little bit the boundary so that I remember that I actually have a boundary. So so the original boundary is this black circle that I have here. The little punctures here are the anti-Stokes directions, and I still have this boundary neck that I'm introducing just to remember that I have a boundary. So this is what I'm calling the surface X plus. So it has, if the original surface had K punctures, this one has K punctures, and plus near each of the K punctures, I need to puncture a bunch of times for all the anti-Stokes directions near those, near this original puncture. And now if I look at the analytic covariantly constant local sections in the flat meromorphic G bundle of irregular type Q on the original compact surface, then you get a locally constant sheaf on this X twiddle guy, which is a locally constant sheaf of very special type. This is what's called a Stokes G local system of irregular type Q. So it's a locally constant principal G bundle on X twiddle, which on the annulus on this yellow neck here, it admits a reduction of the structure group to the reductive group Li, on the finally tau cover of the annulus, on a cyclic cover of the annulus. This corresponds to my extraction of the root for the Puiseux series. And also it has the property that around each of the extra punctures at the anti-Stokes directions that I added, the monodromy is actually conjugated to a monodromy in this unipotent group that was determined by the irregular type, the Stokes group, for any choice of a base point. So the irregular type decorated the surface by these extra groups, a reductive group on each boundary circle, and then a bunch of unipotent groups for each of the anti-Stokes punctures. And I'm looking now at G local systems that on the boundary annulus have a reduction of the structure group to the reductive subgroup Li, and near each of the anti-Stokes punctures has a reduction of the structure group to the unipotent group given by the Stokes direction. These are the Stokes local systems. And so the irregular Riemann-Hilbert correspondence, which really goes back to the work of Stokes and then was reformulated in modern language by Malgrange and Shibuya, and by Deligne and Malgrange, and ultimately by Boauch. This is the picture I'm describing now. It can be formulated by saying that the category of flat meromorphic G bundles of irregular type Q, so this is the Ram guys, is equivalent to the category of Stokes G local systems of irregular type Q. These are the Betty guys that I just described in the previous definition. And these Betty guys, these Stokes G local systems of irregular type Q, are the guys that I would like to study. They give rise to the wild character variety. So if you fix a compact surface X, a divisor D, a group G, irregular type Q, and a collection of conjugacy classes in these reductive groups Li that are given by the irregular type Q, then the wild character variety of irregular type Q is the coarse moduli space, I'm going to denote it by MGQ, of Stokes G local systems of irregular type Q. This is the space I would like to study. It's a space of matrices which are either in G or in Li or in those unipotent subgroups. And they have to satisfy a representation condition that some product of commutators and product of matrices is equal to 1, as before. And there is a restricted version of that, the C-restricted version, which is that the Stokes local systems have formal monodromy around each circle in that conjugacy class. And I didn't explain what the formal monodromy is. So one of the structure results in the classification of meromorphic local systems with a given irregular type says that we can do a formal gauge transformation of the connection to make it regular. To make it with a logarithmic pole at the puncture. In that case, the monodromy of the new regular connection will belong to that reductive subgroup Li, and that monodromy, which is a formal monodromy because it depends on a formal gauge transformation, I'm fixing to be in a given conjugacy class in that reductive group. That's the extra condition that one can prescribe to get a closed subvariety in the moduli of all Stokes G local systems of irregular type Q. So these are the objects I want to study, and I want to talk about their geometry and about their topology. So first I want to talk about their geometry, but maybe I can pause now and ask if there are any questions
So Jim does have a question. Jim, do you want to just ask it?
Sure. I just wanted to, from your description, do the wild character varieties include as a special case just the representation variety of the orbifold fundamental group of just an unpunctured orbifold Riemann surface?
Yeah, so already the tame ones include the orbifold fundamental group.
Oh, those are tame already.
Yeah, those are tame, yeah. The wild ones, they have additional condition that this monodromies around the extra punctures that correspond to the anti-Stokes directions belong to these very special unipotent groups which are the classifying the Stokes matrices that give a wall crossing really for convergent solutions on sectors. So they're more complicated, but the standard orbifold, fundamental group representations, they correspond to the tame character varieties.
Thanks.
It's just a condition for the local monodromy around the puncture being finite order. Yeah, so let me talk about the geometry. So I want to talk about how can you make these varieties nice and realize that they actually have Poisson structures or symplectic structures. So if you fix the data that gives you a wild character variety, a compact Riemann surface, a bunch of punctures, a group, and a collection of these Laurent tails, and a collection of formal monodromies, then Boauch originally, and Boauch and Yamakava in full generality, proved that the smooth locus of the wild character variety is actually algebraic Poisson variety. And the symplectic leaves in that algebraic Poisson variety are the C-restricted wild character varieties, the ones that you get by fixing the formal monodromies. And in fact, Boauch and Yamakava, they gave a very clean quasi-Hamiltonian description of these symplectic leaves by writing a space of matrices with a group-valued moment map and a symmetry group and identifying these varieties with the quotient. So this is the classical story. And the story I would like to talk about now is what do we do when we go on the boundary, when we go away from the smooth locus. Well, one thing that Boauch and Yamakava actually proved is that if you choose your irregular type or formal monodromies generically, so there is a stability condition actually you can impose on the irregular types, on these Laurent tails that I fixed, and on the conjugacy classes of the formal monodromies. And if they happen to be stable, then Boauch and Yamakava actually showed that the whole character variety or the restricted character variety, they're all smooth. Of course, you still need to prove that stable irregular local systems exist, but so it could be empty, but it's smooth. So proving existence is a separate question, which they also looked at, but it's actually a bit harder. But the proof, so this is actually quite nice because that shows that you can get a lot of those Poisson algebraic varieties, smooth algebraic varieties, or symplectic smooth algebraic varieties from this construction. But the proof is still kind of mysterious in some sense, because as I said, their construction is quasi-Hamiltonian. There is no intrinsic deformation theoretic or cohomological reason of why the symplectic form on the restricted character variety or the smooth part of the restricted character variety should be non-degenerate. So you've all seen unramified or tamely ramified character varieties, and we're all familiar of why the symplectic form is non-degenerate there. The Goldman symplectic form on the unramified, say, character variety is non-degenerate because of Poincaré duality with twisted coefficients on the surface. And for for tame character varieties, you actually can find a topological reason. It's again Lefschetz duality on the surface with boundaries with twisted coefficients. But for the wild ones, there is no obvious deformation theoretic or cohomological reason, which makes it hard to say what happens at the singularities. So what I'm going to describe now actually handles both questions, explains what the cohomological reason for non-degeneracy is, and explains that it extends across the singularities. So the goal of the little story I'm going to tell you now is to construct Poisson structures everywhere on the wild character variety, including the singular points, describe the symplectic leaves, as presumably and it will be indeed the restricted character variety, and then find both the quasi-Hamiltonian and cohomological reason for the existence of those symplectic structures at the singular points. And finally, I would like to extend the whole story to higher dimensions. And in fact, the way I'm going to construct the symplectic structures does extend to higher, and Poisson structures does extend to higher dimensions, wild character varieties in any dimension, but I'm not going to talk about this today. Okay, so this is the goal. And the approach, of course, is to resolve the singularities. And you want to resolve the singularities in a minimal way so that the Poisson and the symplectic structures extend to the resolutions. And the way I'm going to do that is slightly non-conventional. I'm not going to start blowing up to resolve the singularities. What I'm going to do is I'm going to introduce structures on these character varieties, extra structures, geometric structures, so that when I take those geometric structures into account, the new object that I'm going to get is going to be naturally smooth. So these resolutions are just coming from refining the moduli problem that I was considering, the moduli problem for representations, wild representations of the fundamental group or wildly ramified connections. And the way you refine that moduli problem is to allow the parameter space for your objects, your connections or fundamental group representations to be not schemes, but to be stacks, and in fact to be derived stacks. So I'm going to allow stackiness, and I'm going to allow extra nilpotents in the function theory, which sit in negative cohomological degrees, and those guys together are going to be enough for me, that they're going to arise naturally in parametrizing representations, and they're going to be enough for me to actually resolve the singularities. In fact, they're canonical resolutions, refinements of these character varieties, which are not schemes, but are derived algebraic stacks. And they're what's called derived algebraic stacks, which are locally finitely presentable, which means that they have perfect tangent complexes. And in derived algebraic geometry, this is exactly what the analog of smoothness is. So the infinitesimal structure of those guys is not given by vector fields, but it's given by a complex of vector fields. But that complex is locally a complex, finite complex of vector bundles. And that's what smoothness really means in this world. And that's enough to actually be able to talk about symplectic geometry. So let me first say what happens in the unramified or tamely ramified case, which are easier. So if you look at the unramified or the tamely ramified variety moduli of local systems, of geolocal systems, it has a natural actual refinement to a derived stack, which is the mapping stack is a derived stack from X to BG, where X is just the complement of the punctures. The straight X is just the complement of the punctures in the compactified guy. And now there is some key observation here, which is that the classifying stack of a reductive group, it's actually symplectic. It just happens to be shifted symplectic. So any killing form, any non-degenerate invariant form on the Lie algebra corresponds to a two-shifted symplectic structure on the Artin stack BG. And a mapping stack from an orientable space with orientation dimension D to anything which is symplectic with a shift is actually symplectic with a shift which is the original shift minus the dimension of the orientation. And since we're dealing with a surface here and BG is two shifted symplectic, the mapping stack will be just symplectic with zero shift. And so what happens is that this symplectic form, which is really the killing form on G, symplectic form on BG, induces a zero-shifted symplectic form on the unramified character variety and a Poisson structure on the tamely ramified one. And in fact, if you fix the monodromy classes for the tamely ramified one, those are the symplectic leaves for this zero-shifted symplectic structure. So because it's a mapping stack in the unramified or the tamely ramified case, the symplectic structure on the target, which is the classifying stack of G, induces a symplectic structure or a Poisson structure on the derived moduli of local systems, tamely ramified or unramified ones on X. This unfortunately doesn't work for the wildly ramified one, because for the wildly ramified one, it's not a mapping stack. But it is a stack of sections. You cannot describe it as a mapping stack to some fixed classifying stack, but there is a sheaf of stacks over the surface X plus, this extra punctured surface that I described, which is determined by the group G and the collection of irregular types Q. And it's a constructible sheaf of stacks on the surface X plus, and the global sections in the constructible sheaf of stacks is the stack of G local systems. So if you take the derived global sections, you get the derived stack of G local systems, of Stokes G local systems. And so it's not a mapping stack, but it's a stack of sections in a constructible sheaf of stacks. And that actually allows you to construct the Poisson structures and the symplectic structures. So this classifying sheaf of stacks is what's called the Linmogram-Stokes sheaf of Artin stacks that classifies G local systems of irregular type Q. And what it is, I'll describe it in a second, but the key feature that we want to observe for it is that along the fibers of this constructible sheaf of stacks, we have actually a natural zero-shifted symplectic structure, which has values in the dualizing sheaf of the surface X plus. And that actually allows you to say that on the global sections, you get a Poisson structure or a symplectic structure. So the Linmogram-Stokes sheaf, it looks like the following creature. So if you take your surface X plus, so remember, it was really a stratified surface. It had this inner stratum, which was the original surface X. It had this necks, this yellow necks that I introduced around each puncture. And then on a circle that separates each neck, there were punctures that corresponded to all the anti-Stokes directions. So these are these green dots. And the Linmogram-Stokes sheaf that parametrizes the data that classifies an irregular local system, it's a sheaf of stacks, which on the big inner stratum is just BG. On each of the yellow necks is B of these reductive groups L's that the irregular types gave me. On each of the arcs that were given by the anti-Stokes directions, it is B of a parabolic for G. And that parabolic is not arbitrary, it's a parabolic whose levy is the given reductive subgroup L. And at each of the points which separate two of the arcs, you have to put B of the intersection of the two parabolics, the one corresponding to the left arc, the other corresponding to the right arc that comes into that. So the collection of the constructible sheaf of stacks that you want to that you need to put in order to understand the Linmogram-Stokes, the Stokes G local systems of irregular type Q, it's governed by this type of stack. And Ezra had a question, so maybe I'll stop for questions now.
Oh, thank you. Hi.
Hi.
I'm just wondering if this picture, it somehow looks like a some sort of Lagrangian, or I suppose more co-isotropic correspondence between BG and BL, thinking of them as...
Yeah, it does. So there is a theorem that I'm gonna state, which at the end says, so remember I said that the key feature of this guy that I just described is that, so it's a sheaf of stacks on X plus. X plus is a stratified space. So this is a sheaf of stacks on X plus, and it has a relative zero-shifted symplectic structure with values in the dualizing sheaf, the Verdier dualizing sheaf of X plus. That statement, that it has a relative zero-shifted symplectic structure, actually is the statement that says that going from stratum to stratum, the nearby cycles in this sheaf of stacks is a Lagrangian inside so the nearby cycles is symplectic, and the actual value of the sheaf of stacks on each stratum is Lagrangian in this symplectic nearby cycles guy. So it's like a system of Lagrangian intersections. In fact, it's a system of Lagrangian intersections going from stratum to stratum in dimension.
Cool.
That's the statement that this thing is relatively symplectic.
Okay, thanks.
Other questions? Okay, so let me just tell you the theorem. The theorem is that the two-shifted symplectic form on BG that I described before, corresponding to the Killing form, extends canonically to a relative kx valued zero-shifted symplectic form. So that's this statement that we were just discussing. The relative form induces a zero-shifted Poisson structure on the derived moduli of Q-type Stokes local systems. And the symplectic leaves are exactly the C-restricted Stokes local systems. And in fact, these statements 2 and 3 in the theorem are a consequence of a general push-forward theorem. So what we actually proved, we proved the characterization of relative sheaves of stacks that have relative shifted symplectic structures with values in the Verdier dualizing sheaf. And we proved that if you have a stratified map between stratified spaces, which is proper, and you push forward a sheaf of stacks that has a relative symplectic structure, the push forward sheaf of stacks has also a relative symplectic structure, which is the push forward of the relative symplectic structure. So this statement about getting Poisson structures from global sections is just a special case of this push forward theorem, which is some kind of a fudged up version of symplectic reduction. It's just a collection of a sequence of symplectic reductions which are governed by some stratification on a stratified space. But for the purposes of the present discussion, this is the theorem. The theorem is that the derived stack of G-local systems, Stokes G-local systems of irregular type Q is smooth and Poisson, and the derived stack of G local systems of irregular type Q, which are with formal monodromy in a given class C, is a symplectic leaf. Okay, I misspelled Poisson here. But, okay, so this is the end of this story, and I now want to switch gears and talk about the topologies of these guys. Maybe we already had questions, maybe, so I'll just move on with the topology so that I can actually say some interesting things about the topology, and we can circle back to questions afterwards. Okay, so before I talk about the topology of the wild character varieties, I want to talk about some classical thing that people are actually very familiar with, and I may have been familiar with it a long time ago, but Eric Sharp actually reminded me about it recently. And because people are familiar with it, maybe it will give you some way to anchor about the question, the complicated question that I want to ask and answer later on. So here is the classical thing. Suppose that you have a smooth compact surface X of genus G and a finite group G. So there is this problem which, for surfaces of genus 1 was actually asked by Riemann, and in general was asked by Hurwitz and probably many other people from around that age, which is, how can we count all unramified G-Galois covers of X up to isomorphism? And I want to reformulate this question. And this is a question about computing an Euler characteristic. The Euler characteristic of the moduli of flat G bundles on the Riemann surface X. But I want to write it in the correct way. In fact, the way it appears in physics. So the moduli of flat G bundles on X, it's really a finite set. But that finite set is a stack because G bundles, flat G bundles on X or G-Galois covers of X, they have automorphisms. So what I really want to count is the orbifold Euler characteristic of that set. And this is actually something that's very familiar in topological sigma models. It's the orbifold partition function of the 2D digraph-Witten theory with gauge group G. So this is the question that I want to ask now. What is the orbifold Euler characteristic of the moduli stack of flat G bundles on X for a compact surface X and a finite group G? And it is really the same as this question of Riemann, because this stack, it's really the stack quotient of the finite set of homomorphisms from the fundamental group of X to G by the conjugation action of G. And so if you want to count if you want to compute the orbifold Euler characteristic of that, which is a rational number, well, you take the orbits for that action, sum over orbits. So you have conjugacy classes of homomorphisms from pi1 of X to G. And you just need to weight those by 1 over the size of the automorphism group of each homomorphism. And of course, by the standard Brouwer formula, this is the same as taking the cardinality of all homomorphisms from pi1 of X to G divided by the order of G. So if you just wanted to count the G-Galois covers without the isomorphisms, you counted them, because if you compute this Euler characteristic, it gives you the cardinality of all homomorphisms. So this is what I want to compute. And we have formulas for this. So the first formula is actually due to Frobenius, who found the formula for G equals 1. So this is just a finite group, and you're counting up to conjugation the number of commuting pairs of elements in the group. And Frobenius actually proved that this is the number of irreducible representations of the group G. Okay, so this formula, it's a great formula. And if you think about it for a second, you'll figure out how to prove it. But it's not completely obvious how it generalizes. In fact, it's not obvious at all. And it wasn't proven until 1978, when Mednich actually proved it. And he gave a formula for any genus, even for genus 0. And the formula is that the orbifold Euler characteristic of the flat G bundles on X is given by, so this is the digraph-Witten partition function. It's given by this expression. You take a sum by conjugacy classes of irreducible representations of G. And then you need to sum up the dimension of the representation divided by the order of G to the power of the Euler characteristic of G, of the surface. So this gives you again a count of all unramified Galois G covers of the Riemann surface by some representation theoretic gadget. So it depends, it's a sum over representations of the target group. And the only way the surface enters is through this exponent, which is the Euler characteristic of the surface. So this is the model of the question I would like to ask. I would like to ask the same question, find the Euler characteristic of the irregular, maybe C-restricted character variety, the wild character variety. So you expect some formula of the same kind. It's going to be a sum over representations of the target group. It will depend somehow on the irregular type and on the local monodromy. But at the end of the day, the surface will only enter through some expression involving the genus. Okay, so now I want to explain what the answer is and how to get it. And of course, in order to get the answer, I mean, there are conjectures for that answer. The most general one is due to Hausel, Merep, and Wong, which came from numerical experimentations and computations with the Weil conjectures over finite fields. But an explanation for those conjectures, and in fact, a strategy for proving them, comes from physics. So I want to talk about this physics strategy. And in the physics strategy, we are going to use a bunch of dualities in order to get the formula for those Euler characteristics. So we are going to rewrite the wild character varieties by some homomorphism as a different moduli space, as a moduli space of parabolic Higgs bundles on the surface with irregular singularities. Then we are going to use some duality with gauge theory in order to rewrite this moduli of irregular parabolic Higgs bundles as a moduli of sheaves on Calabi-Yau threefolds. And this moduli of sheaves on Calabi-Yau threefolds, by some wall crossing mechanism, we are going to relate to a moduli of Pantev-Thomas stable pairs on a Calabi-Yau threefold. And those guys, we are also going to relate to torus links. And if you trace through all those equivalences, you can actually get numerics. So you can get Euler characteristic of wild character varieties converted to information about refined link invariants or refined knot invariants, which you can extract from Chern-Simons theory. And so here are the mathematical conjectures or theorems that you need in order to go from any one of those to the next stage. So the first transition is the wild non-abelian Hodge correspondence and the P equals W conjecture. The second transition is the spectral correspondence and wall crossing. The third transition is Gopal-Kumar-Vafa expansion for Donaldson-Thomas invariants. And the last transition is the Blonkov-Schende conjecture, which, in fact, the part of the Blonkov-Schende conjecture you need here is being proven already. And the physics version of those transitions, so maybe before I say the physics version, let me say what are we relating by those transitions. We want the Euler characteristic or the Poincaré polynomial. In fact, it's going to be the mixed Poincaré polynomial of the wild character variety. And we are going to transport that to a perverse Poincaré polynomial by the Hodge theory and P equals W conjecture. Then we'll use the spectral correspondence and wall crossing to convert this to refined Donaldson-Thomas invariants. And then we'll use Gopal-Kumar-Vafa expansion to convert this to refined Pantev-Thomas invariants. And we'll use the Blonkov-Schende conjecture to convert this to refined Kohler-Link invariants. And in the physics language, of course, these steps 3, 4, and 5 are computing, counting BPS invariants. So supersymmetric configurations of D2, D0 branes on the Calabi-Yau threefold, or supersymmetric configurations of D6, D2s, D0 bound states on the Calabi-Yau threefolds, or refined Chern-Simons invariants. Okay, so let me set this up a little bit. So the group I'm going to work with now is just going to be GLR. The pole divisor is going to consist of single point, just for simplicity of describing what's going on. The centralizer, so this is the group L, the Levy group L that I was talking about before. It's going to be given by a partition of R. So it's going to be a product of diagonal blocks of size mi. And I'm going to assume that it's just the centralizer of the last coefficient of the pole. And the formal monodromy is just going to be a block diagonal matrix, which is going to be the conjugacy class of multiples of the identity, where these phases here are just pairwise distinct complex numbers. So I'm just going to concentrate on that character variety. And my question is how to understand the topology of that character variety. So that's one of the stable ones. So that one is entirely smooth. And I would like to understand its topology. And the question is how to compute its Euler characteristic, or slightly more information, the Poincaré polynomial. And in fact, I'm going to refine it. It's going to be the mixed Poincaré polynomial. So it's an algebraic variety, in fact, an affine algebraic variety. Its cohomology has a mixed Hodge structure, and I'm going to grade the Betti numbers. I'm going to grade the Betti cohomologies by the weight filtration, by the associated gradient with respect to the weight filtration. And so I'm going to get a bi-graded polynomial, the cohomological degree and the weighted degree. And that's the weighted Poincaré polynomial, the mixed Poincaré polynomial, which is a polynomial in two variables, u and v, that count. So u counts the weight grading, and v counts the cohomological grading for the mixed Hodge structure on the cohomology of the character variety, which is a smooth, non-compact affine algebraic variety. So this is the guy I would like to compute. That's the analog of discounting question that I was describing for the finite covers. And so the wild non-abelian Hodge correspondence, which in various situations, in various degrees of generality, was proven by Descartes, Bouarch, Witten, and Saba and Mochizuki. It says that irregular flat connections correspond to irregular Higgs bundles. The modular spaces are homomorphic. And in fact, if you fix the formal monodromies, they're hyperkähler and they're related by hyperkähler rotation. So I'm going to use that and convert the question about computing the Poincaré polynomial or the weighted Poincaré polynomial to a question about computing topological information for the moduli of irregular Higgs bundles. And the P equals W conjecture of the Cataldo-Causalli Migliorini for these irregular character varieties, its extension to the irregular character variety says that the steps in the weight filtration for the character variety correspond to the steps of the perverse Leray filtration for the moduli of Higgs bundles. So you take the Hitchin map for the moduli of Higgs bundles, use the Leray filtration, the filtration in the abutment of the Rayleigh spectral sequence for the intersection cohomology along the fibers. And that filtration gives you a filtration on the cohomology of the total space. And the P equals W conjecture says that the weight graded pieces or the steps in the weight filtration are the same as the steps in the perverse Leray filtration. And so we would like to compute the perverse Leray polynomial for the moduli of Higgs bundles. And here is the answer. So this is this conjecture of Hausel, Merep, and Wong. It says that you can write a partition function. So it's a completely explicit function, very similar to the one of Mednick that I described, the Digraph-Witten partition function for the finite groups. So it's a product, it's a sum over representations of the general linear group. So these lambdas are Young diagrams. They're partitions of R. So you have a sum of representations, irreducible representations of the general linear group of some polynomials in two variables, Laurent polynomials in two variables. The first one, omega gn lambda z w, so it depends on g and on the partition lambda, on the representation. And this is the formula for it. It's a modified Hooke polynomial. So it depends on the Young diagram lambda, it depends on the number g and on n. N was the order of the pole. And you know, it has terms which depend on the size of the matrices I'm dealing with, on the genus. They appear as exponents. And then there's some monomials or differences of monomials where the powers of those monomials correspond to the arm length of a box in a partition or to the leg length of a box in the partition. But in any case, it's some explicit polynomial that depends on the partition with terms which are labeled by the boxes in the partition, which is the representation of the group G. X is, of course, a sequence of variables formal variables that we're using for counting Schur functions. And this H twiddle lambda x zw is just the modified McDonald polynomial. And I'm not going to write the formula for the modified McDonald polynomial, but it's a standard creature in the representation theory of the symmetric group or the general linear group. So again, it's an explicit polynomial in Z and W, depending on the partition. So there is this Hausel-Merep-Wong partition function given by this expression. And the conjecture that Hausel-Merep and Wong made is that if you expand this partition function or the logarithm, the free energy corresponding to it, so the logarithm of that partition function into the coefficients given by the monomial symmetric functions in the labeling variables x, then these coefficient polynomials are up to reparametrization exactly the weighted Poincare polynomial of the irregular character variety for the regular class C given by the partition. So they only made the conjecture for the partition, the full partition, the one that partitions into a diagonal system of boxes. And we, as you will see, we refined that conjecture, and we actually gave a strategy of proving it and could verify it by some vocalization in some cases for low for small values of the boxes in which the partition breaks. Actually, I'm out of time, so I probably I'm just going to stop here. I'm just going to say that there is this strategy that I described, and you can follow it, and you can actually get a formula in general for this weighted Poincare polynomial, which you can prove in some cases by actual localization. So we proved some of the steps in the strategy, but not all of them. In particular, we're still missing the P equals W conjecture part, and the last part, which is the Gopal-Kumar-Vafa expansion. But we proved, so maybe if I go to the, we proved this part, which is the spectral correspondence and the wall crossing part. We actually traced quite carefully by using the refined version of the Kontsevich-Soibelman spectral correspondence for irregular Higgs bundles. So sorry, I'm going to stop here because, yeah, I'm out of time. So questions?
Still have a couple of minutes, Tony.
Well, I don't think I can really say. I mean, you know, there is how you relate this to the not invariants by looking at links of singularities of spectral curves, but I don't think I have time to explain that. So I'm going to stop here, and people can look at the slides.
Tony, maybe you can send the whole slides, including the.
Yeah, I will send the whole slides. Yeah.
Yeah, great.
All right, well, let's thank Tony. And in the chat, there are a couple of historical remarks. I don't know if you want to start with those.
Oh, sure. Yeah. Let's
So
see.
the results that you said are due to someone in the 70s, probably now 70 years older.
Okay, I didn't know that, but
Burnside and Shore.
It was actually an exercise in Burnside's group theory book. I mean, he phrased it in terms of, you know, elements in a group satisfying the commutator relation. But anyway, that doesn't really matter. Maybe Tony, while I'm on, can I take a quick question, ask about the threefold geometry? So when you convert this into a threefold geometry, are you on like the total space of the canonical over the curve cross a
line,
C,
yeah.
or are you on something?
Yeah. No,
we're on
line. We're on the canonical space. Yeah.
How much of this story can be generalized to, say, just general local curves, where now maybe instead of a Hitchin system with a single Higgs field, you have like commuting Higgs fields? I made this a little different direction from what you're asking, but from what you were talking about, but I have that question.
I mean, I don't know if you can do it for a general local curve, but certainly there are irregular character varieties which will give you more complicated Calabi-Yau threefolds in this program. And those will correspond actually to real forms of the group. So if you take the irregular character variety corresponding to real forms of the group, so you need to be a bit careful of how you define the corresponding moduli problem, but there is you can think about those guys as representations, irregular local systems with values in G with a reality condition corresponding to a real structure on the group. And then the irregular character varieties are actually well defined. And there is an irregular Higgs bundle version of those, and those guys can be rewritten as pairs of commuting Higgs fields or Higgs fields satisfying polynomial equations in some cases. And those lead to interesting different three-dimensional Calabi-Yau geometries, local Calabi-Yaus. But I don't think actually anybody has looked at that carefully or studied that in any detail. It's just that the only way I've thought of how to get different Calabi-Yau geometries in this setting.
Other questions?
Yeah. Tony, may I ask you, a couple of questions. So first, I do not understand the relation between this very abstract DG beginning and very concrete end of your talk.
Well, there is no relation, because the first part was about the geometry and dealing with the geometry when you have singularities. And the second part was when you fix the stable case when you actually don't have singularities and try to compute.
No, about the first one, do you have sort of a non-abelian Hodge theory for that DG stack, which you mentioned?
It depends what you mean. The problem is that so in the DG stack there are two refinements that are happening, right? One is the stackiness, the other is the derived structure. And you can ask whether the non-abelian Hodge correspondence extends to give you something like differentiable stack isomorphism or a homomorphism of topological stacks or something like that.
No. I mean, let me just tell you an example for G equal GLN. Then you have an underlying categories for Higgs, for local systems, and so on. So then you can construct a family of categories, sort of a twister family of categories. So they depend on one parameter in CP1. And I naively imagine that you look for DG stack of objects of one of those categories, namely, say, category of bundles with irregular connections.
Right. So the twistor picture certainly exists. What's missing in the twistor picture, when you get the twistor family of categories or the twistor family of derived moduli, it just analytic, or in fact, if you restrict to an open part in P1, an algebraic family of stacks, the problem, the missing part is the twistor sections. Right. I mean, in the twistor space, you don't just need a family of stacks, you also need a real family of sections that trivializes it. So that's the thing that the non-abelian Hodge correspondence is responsible for. And that's the thing that's hard to construct in this derived stacking setting. But in fact, the derived structure is not the problem. The stackiness is the problem. So there is a real problem when you have continuous stabilizers in actually constructing the twistor sections with the stackiness. In fact, there are counterexamples there are no-go theorems for existence of twistor sections. So there is something missing in the way. Whereas if you are, say, at the Linmogram point and you look at the derived structure, you can actually extend the twistor section to include the derived structure with no problem. So that there is something missing in the non-abelian Hodge correspondence because of the stability. There is something missing when you're dealing with stackiness. But if you are willing to frame, if you add an extra puncture and you add a framing for your guys at that puncture, then actually everything works, even with the so you get different Poisson guys and different symplectic structures, but the non-abelian Hodge theory will work in families, will work well for the moduli spaces. Everything will work.
Yeah, and one more small question. It's kind of related to what Brian asked you. It's about 3D perspective. If I replace the cotangent bundle, I mean, something which is related to Higgs bundles via the spectral curve sitting in this particular two-dimensional Calabi-Yau surface, non-compact. If I replace it for any complex symplectic surface, so then you have the Higgs story, which correspond to coherent shifts with pure one-dimensional support. And so, I recently heard the talk of Ben Davison, and he somehow convinced me that P equal W does exist at the level of two Calabi-Yau categories. So then,
well, it's quite possible, but I unless that surface is some surface for which we actually know what the, if it's one of those, yeah, I mean.
CP2 minus cubic.
Right, but we need to know what the corresponding Betty picture is for which
it's not a problem. We've been worked it out with Maxime. It's Fukaya category for wrapped Fukaya category for that complex surface. So this one is not difficult. I mean, modulus.
Right, but yeah, at the moment you have a good Betty picture, I can imagine that there is a P equals W, and then it's just going to be a counting of the moduli space there. But
Yeah, and for that there is a kind of a 3D picture, because you can, as you said, multiply it by a line, so you have 3D Calabi-Yau. You can localize,
Right.
hopefully. So,
Yeah, no, it should work.
okay.
Well, I mean, you know, the localization argument, if you want to actually prove the conjecture by doing some torus localization, then you'll need some torus symmetry of that surface. But if you just want to formulate a conjecture, you can definitely formulate it.
Okay. All right. Thank you.
Are there other questions?
Oh, Lev has a question.
Oh, please, Lev, yeah. You're muted. You need to unmute yourself.
Sorry. It's a simple question. So you associate a torus knot to your point where you have this wild character, right?
Yes and no. Yeah, I mean, so the way so there is some strange duality happening here, right? So there is indeed a knot that corresponds to the stock structure at the ramification. But in this picture, in the Chern-Simons conjecture, which one uses to do the calculation, there is a different knot, which happens to be actually the same knot, but I actually have no clear explanation why, which appears when you take the spectral curve describing the type of characters that you're of geolocal systems that you're looking at, and that spectral curve actually has a singularity. Some other singularity which comes from a torus localization, and the link of that singularity is the torus knot that's associated to the picture in the conjecture. It does happen. So in the cases where we can actually check the conjecture by torus localization, it does happen that the two links are the same link or are equivalent links, but I have no explanation of why.
May I ask a little bit more?
Okay.
So in this torus NM,
Mm-hmm.
N would be, I suppose, the GLM that you're using,
Mm-hmm.
and M would be the order of the pole.
N is the order of the pole, yeah.
And, but then you have some extra data which describes the singularity. So how is it reflected in the?
Yeah, so you're looking at colored, not invariants, not so yeah. I mean, if you look at the
it's the color.
It's colored, yeah.
So you have your Q's. You had a complicated data which describes the singularity. How do you convert it? Oh, so the Q's are discrete parameters, in fact. Because the coloring would be just a choice of.
Well, they're discrete in the sense that, you know, they're labeled. Remember, they're labeled by Levy subgroups or some parabolics up to conjugation.
So all that matters to describe this singularity is a Young diagram M and N.
Yeah.
So may I ask a little bit more?
Mm-hmm.
So it happens that to such a torus knot with a coloring, people can associate a sheaf over the Hilbert scheme of endpoints.
Mm-hmm.
So I wonder if you will reproduce your formula if you do a calculation along the following lines. So you take the sum of exterior powers of cotangent bundle to the Hilbert scheme and raise it to the power G, if I'm correct, where G is the number of handles.
Yeah, you know, this is actually how Schende-Truman and Zassel did the conjecture. So there is this Oblomkov-Schende conjecture, which I mean you can look somewhere in the slides. I talk about it, but this calculation that you're talking about, it's really how you actually how the modified McDonald polynomial appears. The modified McDonald polynomial is exactly this Adams operations on the universal bundle of the Hilbert scheme. So in fact, I have slides about it, but you can look. I mean, I'm not going to go through them, but you can look at it. So there is slides about it.
So it's somewhere in your talk slides, but down the line.
Yeah, right. Yeah, but yeah, so there is this Oblomkov-Schende conjecture, which actually relates it to an equivariant Chern character calculation for wedge powers of the universal bundle on the isospectral Hilbert scheme, and this is the reason of why the modified McDonald polynomial actually appears in this formula. And of course, you need to relate that to the torus, to the cohort not invariants.
So I think that from the physics perspective, you're doing, if I understand it correctly, you have a free Calabi-Yau and you have an extra C2, which is in the form of Taub-Knot, and an extra 11th dimension. So you compactify the Taub-Knot by the U1 rotation.
Yeah.
But alternatively, you could compactify your Calabi-Yau by rotating the fibers. So your Calabi-Yau is something like local curve. Is that how you call it?
It's a local curve, yeah.
So you can rotate its fibers in the opposite directions. So instead of compactifying C2 or Taub-Knot, you can compactify the fibers of the local curve. And then I think from the string perspective, this would reduce the calculation to taking cohomology of the product of the bundles over Hilbert scheme that I mentioned.
Yeah, because it's slightly more. It's like nested Hilbert scheme, but yeah, I mean that's the physics argument.
No, it's not the Oblomkov-Schende. It's something different.
Yeah.
Schende are in fact on the side of compactifying Taub-Knot. So this would be totally different.
Yeah, this is slightly more refined, but it's the same principle. Yeah.
Tony, could I just get one more in real quick?
Sure. Yeah.
So my understanding of your passage into the threefold geometry, I think that's for G is GLN. Do you have is there a threefold story, a threefold geometry story for other groups, specifically the SP or the Os?
There should be for classical groups, but So for classical groups, or if you also decorate things by an extra representation of your group, right? You can always convert everything to spectral data. So you should be able to get the same picture, but so it's still going to be the same Calabi-Yau, but the sheaves or the Poincare-Thomas pairs you're going to be looking at are going to have supports with
like equivariant with respect to something.
So
right?
there will be some involutions.
It seems like it should be on like the orbifold Calabi-Yau that I get by quotienting, but I haven't been able to actually make that work.
You can do that, but I mean, you can do that, but it's the same as just looking the same at that guy with, I mean, there is an involution acting, and I mean, you can just take equivariant guys with that involution, with respect to that involution, but yeah, I mean, I don't think anybody has looked into that. In fact, they're not even conjectural formulas for other groups. I mean,
yeah.
In principle, even in the unramified case, you should be able to actually write down a formula for arbitrary groups by following what Hauzel and Rodriguez-Viegas did. You take this formula, you go to a finite field. Now you're dealing with representations in a Chevalier group. You take the formula of whatever Burnside, sure, and then use the Weil conjectures to guess what the general formula is going to be.
Well, and part of the ethos is that same counting stuff shows up in the orbifold topological vertex, because you can do the PT side sort of using the orbifold topological vertex. But like I said, I haven't been able to make this work in the in these.
Yeah, I
SP
haven't even
groups.
tried, so you're far ahead of me.
Tony, going all the way back to the beginning.
Uh-huh.
So you say that you can you give some intuition about why we should expect to be able to put everything in the maximal torus or in the Cartan?
Oh,
So
no,
for
that's
example, if you start just with a pure second order term, nothing else, but that second order term is a nilpotent. So you're saying that by adding some first order term, you can make the second order term be diagonal?
you know, I mean, we know that very well, say, for Higgs bundles. I mean, you know, for gauge transformation, it's slightly more delicate because you're dealing with standard, what is it called? Canonical forms of matrices in the differential Galois group. But for Higgs bundles, right? I mean, you can ask the same question. If you have a Higgs bundle with a higher order pole, the claim is that up to automorphism, you can always make the higher part of the pole be in the Cartan, and that's just the statement that, you know, okay, you're allowing extracting root, so you're working over the Puiseux series, the algebraic closure of the Lorentz series, right? But then you can put the thing in a Jordan canonical form, and off diagonal part is homomorphic. It has ones on both the diagonal. So the polar part is diagonal, and the off diagonal part can be whatever you want. It's homomorphic. It's the same statement. You just need to do it in the differential Galois group.
Great. Are there any other questions? So the next talk is going to be in 2 weeks by Holland. And let's thank Tony again for a lovely talk.
Thanks, Tony. That was really fun.
Thanks, guys. So I'm going to stop sharing.
And I'm going to stop the recording.
Dave, do you want me to email you the file, or do you want me to just put it in the chat? Dave is gone, so.
It was gone. Just mail it to me, CC it to him.
Okay. All right.
All right. Job well done.
Okay.
As usual, you're thinking about the same things I am, but in vastly more generality. I'm still in my little corner trying to understand my piece of it.